All right, good afternoon, everyone. So any questions on the midterm, about the midterm this Friday? All right. Okay, so we were talking about how you can use transfer learning to load a pre-trained network with all the weights in it, and then just learn a few of those weights to customize it to your task. And we said there's a whole bunch of these pre-trained networks available, and these are also kind of ordered in time in terms of when they were developed. And just by going through them, we can learn about a lot of the tricks that were learned over time, and learn about some networks that might be good for our applications. So we started with VGG. VGG was an improvement over the AlexNet that we discussed. Took the error rate from 15% down, basically halved it. However, in going from AlexNet to VGG, the number of parameters in the network went from 60 million to 180 million, and at the same time, researchers, they noticed that the deeper the networks were getting, the better they were working, but they realized that they couldn't keep scaling the coefficients this way. So then they started to work on making more efficient networks, and one of these is GoogleNet or Inception version 1 that had only 5 million parameters, which is a huge reduction compared to the previous ones, and still managed to beat VGG 16 by a little bit. And this was based on Inception modules and a few other tricks. The next big breakthrough was in 2015. What researchers were starting to notice is that as these networks got deeper, not only was there this issue with memory and computation, but actually training them was getting more and more difficult. So the authors of the ResNet paper that basically figured out a way of solving this problem referred to this as the degradation problem. So they pointed out that degradation was different from overfitting. So if you were experiencing overfitting in your network, what that would mean is as the network gets deeper, you would see the training error get better and better as the network gets deeper, but the test error would get, not as good. But they were actually seeing that even the training error was getting worse as the network was getting deeper and deeper. And then they tried to explain why this was. Their explanation was that if you imagine that layers, and I'm talking about like a layer consisting of like linear activation, maybe pooling. If those layers could act like an identity operator, then there would be no issue with tacking on extra layers to make your network get deeper and deeper, because essentially by tacking on identity layers, you're not changing anything, right? And then they said, well, so therefore, if when we tack on these learnable layers, things are getting worse, it must be that these new layers we're tacking on cannot act like identity layers. So does this make sense? What is preventing these networks from acting like identities? So I don't know, I haven't used my attendance sheet in a while, so let me see. Is Jacob Brees here? Yeah. Okay. Yeah, so what do you think? Like, what part of the network is causing this issue where it can't act like an identity? What part of it, the layer?
Well, I assume it's going to be the way the layers,
because let's say we're talking about a convolution layer. Is it impossible for a convolution layer to act like an identity? So, anybody else? So the answer, actually no, convolution layer can be identity. So how do we get a convolution layer to act like an identity? What would the kernel be?
One in the middle, and then
Yeah, it'd be like a spike. like all zeros in a spike, you convolve that with a signal, nothing changes, acts like an identity. So that's not the issue. Let's see. What about the activation? Is the activation acting like an identity? Yeah, it's nonlinear. The ReLU, which is what everyone was using, actually just clips off the negative part of the signal, right? So that certainly is not acting like an identity. You can kind of get it to act like a biased identity if you in the network before, if the layer before the ReLU, you just shift it. So now the ReLU would be like there, and it kind of acts like an identity in that region, except you can see it's identity, but it's adding something. So in any case, they said, the issue here is that we can't get these layers to be like identities. What can we do? What can we do to our network architecture to, force an identity operation? And what they did is they proposed to add this sort of bypass path. And so here you can see, like, now, in order to make this thing act like an identity, what would we do? Let's see. So is Heriberto Nurse? Yeah. What would we do to make this thing act like an identity? Well, this part is like identity, right? It's just passing the data. So how do I get this to be 0? So I can adjust things here. So if I can make this 0, does that make sense? The information just flows around it. It doesn't go through here because we've made that 0. So let me see. Akash Patel? No? What about Alec Robertson? What about Fatima? What do you think? How could I get this to act like 0? Set the weights to 0. Right. So if the weights are 0, then you can see that this whole thing, this doesn't pass anything. This whole thing acts like an identity. So we can tack on, as many of these blocks onto our network as we want, and we can easily learn weights that make that block act like an identity. So there should be really no cost to adding as many of those as we want. And if there is some benefit to having them there, we will learn them. We will learn, versions of the weights such that that thing actually helps. And so that way we should be able to make networks that are as deep as we want. And in fact, they were able to make networks more than 1,000 layers deep using this trick. It doesn't necessarily mean that 1,000 layers is the optimal solution because, when you have so many layers, there's so many weights to learn everything. But they showed that there was, no issue with making them longer, really, if you could put up with the computation and the memory and all that stuff. So that was their way of explaining the problem. There's many different ways you could imagine doing this. Like, I don't know exactly why they have a weight, a ReLU, and another weight layer. By weight layer, they mean like a linear layer, like a conv layer, or possibly a dense layer. They could have just put this around the weight layer itself, but whatever. They probably tried several things, and then this maybe worked a little bit better. But overall, this thing, they called this a residual block, and they just tacked all those on. This is often called a skip connection, that thing. Okay, so anyway, with this advance, compared to GoogleNet, which got 6.7%, they were able to have that get 3.6. Now, this is not as efficient as GoogleNet. GoogleNet had 5 million parameters. This is slightly lower complexity than VGG16, which I think had 180 million. So, quite a lot of parameters, but it was winning competitions. So as we go, forward in time, things keep getting better and better. People keep figuring out these new tricks. So later, there were some more interpretations of this that were published that actually explained more precisely exactly what was going on with these networks. And so this is really how we want to think about it. Basically, imagine that we have an arbitrary nonlinear thing here. It could be, like on the previous page, it could be a linear layer, a ReLU, and another linear layer, or whatever. It's just some block. And here we have a skip connection around it. And this building block, in this picture, we're just concatenating that 3 times. So if you imagine that as the data flows through, at every stage, it has a binary decision of whether to go through the skip path or to go this way, you can imagine sort of unfolding this into, in this case, 2 to the power 3 parallel paths. So here, like for example, one way data can flow through is it can just do one big identity. So that's like 1 of 8 possibilities. At the other extreme, it can go through all 3 of those Fs. That would be another possibility. But there's all sorts of other possibilities, like it skips F1 and goes through F2 and F3. So that would be like this one. And so overall, there is 2 to the power L if there's L of these. And so in this case of L equals 3, we have 8. And this is one way of drawing those 8 unraveled possibilities for this residual network. So what's actually interesting is once you start looking at lengths typical of what people use in practice, which might be like 50 layers, 100 layers, you start noticing some interesting things about how these parallel things behave. Like, for example, in this, when you have 3 in this case, we have one path that has depth 3. We have, there's going to be 3 different paths with depth 2, right? I can go through this one, those 2, or those 2. 3 paths of depth 2, 3 paths of depth 1, and 1 path of depth 0. Okay. When you look at a large number like 50 or 100, and you make a histogram of the number of paths, and you make a histogram of this, you find that, I don't know how accurately I drew it, but something like this, that most of the paths, if L is the total number, the max number of paths, you find that most of the paths are L over 2, and there's only one path at 0, one path at L. There are some paths in those regions, but most of them concentrate at around L over 2. Furthermore, when you look at the deeper paths, those over here, because there are so many of them, there are some issues with vanishing gradient and so on, so that those paths, they don't really contribute as much to the final answer. So they did a study of a 110-layer network, and they found that only paths of length 10 to 34 were really meaningful contributors to what's going on. There's a few, that are smaller than 10, but there's just so few of them that they don't really contribute much to the overall number of paths. And the ones greater than 34, there's either not many of them or the vanishing gradient is making them pretty weak contributors. So really, another way to think about this is, again, through this ensembling idea, which says when you do this ResNet sort of thing, you're really building parallel paths of, many different networks at different depths, but most of them have moderate depths, 10 to 34. And these are the sort of numbers that people were, this range is already the kind of depths that people were seeing in previous work. So it's sort of like, okay, what's really happening here is like you have a whole bunch of these networks that are working in parallel to provide a really good answer. And they're not necessarily that deep, the ones that are working in parallel. And they did all sorts of nice experiments to show this. They showed that you can pull out a given network in the middle of a ResNet, and pull out this one, just get rid of it, and the performance doesn't really change very much. It's like the ResNet doesn't really depend on any given one of this or this or this. You can take individual ones out. It doesn't matter too much. And so that was sort of a view that explained more of what was happening with this ResNet idea. And other people took this even further, and they said, well, if that's the case, we can do something like dropout, but rather than doing dropout at the scalar level, the nodes in the network, we can actually drop out entire layers here. We can drop out this entire thing, which has a whole bunch of channels and pixels in it. And we can drop out this. We can drop out random combinations. And that works really well too. That's called a deep network with stochastic depth. That speeds up ResNet training, reduces overfitting, so on. So, this is just an important step along the way. And these days, if you want just a really good, classification network, a ResNet is just one of the choices that people just take out of the box, because it's really great, like a 40-layer ResNet, something like that. Works great for whatever you're doing. Okay. All right. Any questions on ResNets? Okay. So, we saw that there were, we've looked at a few in depth, and let me just kind of zoom out and talk about a few more, but not as much in depth. So inception, there were actually a whole bunch of these different inceptions. We talked about version 1, then there was version 2, version 3. There was an inception with ResNet type ideas in it. They had more efficient inception modules. They had these auxiliary outputs where they would take an output or few outputs in the middle of all these deep layers, and they would somehow come up with a loss that worked not just at the end of the network, but also at points in the middle of the network. This Inception v3 took second place in 2015 competition, whereas this ResNet was first place. Then 2016, the DenseNet. So DenseNet is kind of like taking ResNet another step, where each layer in the network is connected to all previous layers. So in a ResNet, you have this layer, this layer is connected to this and to one before it. But in a DenseNet, you say, oh, let's also connect that to there. And then over here, let's connect this one. For this one, we need to add this. For this one, we already have that, but we need to add this and add that. So that's the idea. So here you have these blocks. So these blocks may only be like 8 deep, but in each block, this guy is connected to all previous, this one to the previous, this one to the previous, and so on. And so this might be 8 or 16 or whatever, and then you have a cascade of those dense blocks. This one outperforms the ResNet. However, it has much greater burden in terms of memory, especially with the backpropagation. So at some point, performance was getting so good that people stopped working so much on the classification performance and they started working more on efficiency. They said, at the end of the day, probably the main place we want to use this is on like a mobile phone, not on some server farm. So, and these things are just too big to do on a mobile device. So we have things like SqueezeNet, which was AlexNet-like performance, but 50 times fewer parameters. 50 times fewer than AlexNet is like 5 times fewer than that GoogleNet. That was 5 million. It's like 1 million parameters, roughly. So that's, a lot more efficient than Inception v1. The next year, an improvement on that, MobileNet. Very efficient in memory computation, very high accuracy. So, so those are, just sort of a recap. All of these guys are available for download with the weights in Torch Prism. And there's more. They've added more, but these are just some of the original ones. Okay, so that sort of concludes the discussion of how these networks progressed over time and what's available in Torch Vision. Any other questions on any of these networks or related convent ideas? No? Okay. So now let's go to PyTorch and let's download one of these networks. So let's download BGG16. And pre-trained equals true means give us all the weights, not just the architecture. And when you do print string model, it nicely formats the architecture for you. And here you can see that there are actually 3 different sections. There's the features section, this average pool section, and the classifier section. Okay, so let's look at each section. The features section has things like conv-relu max pool, so on. So yeah, in general, you have convolution, activation, pooling. Sometimes you leave out the pooling, but otherwise, that's what it is. You can see here input channels, output channels, the kernel size, the stride. If the stride was 2 by 2, that would mean that we're doing subsampling, but no subsampling in any of these. Padding, for a 3 by 3 kernel, a padding of 1 would give you valid mode. So you don't specify valid mode, you actually specify the amount of padding. So that's the features layer, just convolution, convolution, convolution. The classifier layer, you can see that has linear, relu, dropout, linear, relu, dropout, and then one more linear. So in this network, there's an option you could put in a softmax at the end, but there's no real need to. So they don't include one. The number of output features, 1,000. That's what we would expect because this is for 1,000 class classification. And yeah, you can see dropout here is being used with probability of 0.5 in these 2 layers. So the other thing to notice is that the size of the input to this first dense layer is fixed. It's 25,088, right? What happens if I would put in to the input here? What happens if I put in not a 224 by 224 like ImageNet size, but what happens if I put in something twice as big? So let's see, is Zacharias Tebben here? Yeah. So what happens if I put into this input not a 224 by 224 image, but an image that has twice as big? So that would be 448 by 448. What would the size be at the output of all these convolution and pooling layers relative to the 224 by 224? So if I double the input size, would the output size here double, or would it be the same as the original one? Or well, I think it would just exactly double it. So all the convolutions are essentially valid mode, so the convolution doesn't change the size of the image. And then the ReLU doesn't change the size of the image. And then max pool, it always like halves, or some integer reduction in size. So if I start with something twice as big, I'm again going to have it. So I'm preserving that doubling in size. So essentially, yeah, if I double my input image size, then I double the size at the output of the feature layer. It's just twice as big. So what is the issue with that now with my classifier? You see, this guy has 25,088. If I have doubled everything here, it's not going to match, right? There's going to be a mismatch in size. So that is what this average pool layer does. This is the glue that matches the sizes. So this is an average pool layer, so we know that basically just averages what happens in certain ranges of pixels. And this one is set so that no matter what the input image size or feature map size is to the input of the average pool layer, the output is always going to be 7 by 7. And that way, I can handle any image size in this network whatsoever. I can put in an image that's twice as big as 224 by 224. I can put in an image that's smaller. No matter what, this average pool layer will always adjust the size so that the output going into the classifier section is always exactly 25,088 numbers. Okay, so that's the purpose of this. Is basically to handle different sizes. Is that making sense? Okay. So the nice thing about these convolution networks is that they can be used with any image size. Now, if you give it like a tiny image, of course, it's probably not going to work well because you can't really tell what class it is from this tiny image. And if you give it an absolutely enormous image, it might not work as well there too because all of its convolution layers are they're sort of designed for a 224 by 224. So if you give it like a million by million, they're going to be a bit small. They're going to be searching for features for little image behaviors that are kind of smaller than you would see in a 224 by 224. So, but it will work. It won't like give you an error. So that's a nice thing about these convolutional neural networks. Okay, so we have like basically 13 of these conv layers, 3 dense layers, and then the average pool that makes sure that they play well together. All right. Any questions on this? Okay, great. So, all right, so to play around with things, we'd like to get some test images, and there's all sorts of different places to get test images, but if you look at ImageNet, you might not find exactly what you want. However, Flickr, which is a photo sharing site, has a lot of labeled images where you can go in and you can say, I want pictures of people eating a hot dog. And it will give you as many pictures of that as you want. And so that's a nice way to go. It's free. So in order to work with it, there's a demo that guides you through this, but you need to register with Flickr to get some API keys. Once you have them, you have permission to download, and it's relatively easy to do everything. So the way we're going to store these images, we're going to make separate test and train directories and store the images there. And in this case, we're just going to, for this demo right here, we're just going to download images of elephants. So in the lab, you're going to use this and download, I think, bicycles and cars. And then you'll have binary classification problem. So here, And in that binary classification problem, you can retrain the dense layers of something if you want. Or here, we're just going to use a pre-trained network. We're going to grab elephant images, and we're going to see, does this ImageNet network work to classify my elephant Flickr images as elephants? Or does it make mistakes on these elephant images and think they're something else, turtles or whatever? So there's a few other things that we have to do when we work with an ImageNet trained network in terms of normalization. So one of the things we're going to do here is we're going to use this transforms.normalize. And these parameters are what everyone uses to calibrate images so that they look like ImageNet images, to normalize them or standardize them. So these are the numbers of the means in the red, green, and blue channels, and these are the standard deviations. So I don't know exactly where these numbers came from. It could be that maybe you just go to ImageNet and you just look over, all the ImageNet images and you compute the mean of the red channel and it's 0.485. Maybe it's as simple as that. But this is what everyone always uses when working with an ImageNet trained classifier, but bringing in data that's not ImageNet, like bringing in data from Flickr. The other thing we're doing in this step is we're choosing the size. We're setting it at 224. You can go in and you can change the code. You can make it 100. And this center crop just looks at the center 224 by 224. If you want to do 100, you can center crop it. And that will make your code run faster because there's less pixels to process. Or you can add other transformations to this for data augmentation. You could do like horizontal flip, color jitter, whatever you want. And then what you do is you do transforms.compose, and you put these together, and it will first do, I think it does this crop first, then transform to tensor, and finally normalize. So that is it's gonna happen for all your images. We'll go through those pre-processing steps. And then we do the things we described before. You create one of these dataset objects. You then, from the dataset, you create a data loader object. Here's where you set your batch size. And to pull out image label pairs out of your data loader, you just do, excuse me, next iter loader. Okay, so now since our network's already pre-trained, that's the hard part, that's already done. So we can just push our data right through our network. So we put all these PyTorch models, they're either in training mode or evaluation mode. What changes between those modes is, for example, in batch norm, we learned that in batch norm, you first normalize in every channel and layer. You standardize to zero mean unit variance, but then you learn possibly a better shift and scale than 0 and 1. And so in training mode, you learn those things. In evaluation mode, you just use them. You don't try to learn them. So that's one of the things that changes when you're in evaluation mode. There's a few other things like that as well. And then with this with torch no grad, that basically means, okay, PyTorch, we're not training, so do not compute gradients. Don't do any backpropagation stuff. We don't need that. Let's just put our x through our model to get our output. Our output, as we saw, is just a bunch of scores, real numbers. So to interpret them, let's put those outputs through a softmax. So now we get something like a probability distribution. And for the purposes of visualizing what's going on, let's look at the top 3 guesses that our neural network comes up with. And so there's this top K command that basically extracts the top 3. Let's move things to NumPy, and then let's put things in a pandas data frame just as a nice way of plotting them. And here we have our 10 images in our batch, and we're plotting or printing the label of the ImageNet class that corresponds to the most likely, what our network thinks is the most likely class, second most likely class, and the third most likely class for each of these 10 images, as well as the probabilities that come from the softmax. So here you have like around 70%, 28%, and 2%. And you can see that within ImageNet, we have things like African elephant, Tusker, Indian elephant. And in all these cases, its top three are those three. It's not really seeming to make any mistakes. Now, I don't know if, maybe in terms of whether these elephants really are African elephants or Tuskers or Indian elephants, I'm not sure. We don't really have the labels to verify that. But, according to Flickr, these are all elephant images, and yes, our network is classifying them as some kind of elephant. So that's great. So there's actually a typo here. This was for an earlier version of the lab, which did have an error, but so everything is correct in this little this demo here. Okay, so that's just an example of downloading a pre-trained network, downloading images from Flickr, putting them through the network, and verifying that, yes, this ImageNet trained classifier is really working. All right. Any questions on anything here? Okay, so you can, these demos are just great sources of examples if you want to apply this in your own projects or your own research or whatever. Let's look at something else. Let's look at the feature maps that the classifier has learned as you go deeper into the network. So for this, we're going to build a little network called a feature extractor. And this network is going to take in the model, which is going to be VGG for us, and we're going to give it a list of feature layers, which are layers from the feature section, and classifier layers, which are layers from the classifier section. And what it's going to do is it's going to put data through the network, and if we get to a point in the network that is in our list of feature layers, it is going to remember what it saw there, and it's going to concatenate it onto a data structure and give us this data structure at the end so that we can print out, what we saw in those intermediate layers. And so this is how it works. So this is just the initialization of it. So it just saves the model and the feature layers and the classifier layers as internal variables. More interesting is the forward layer. So you take in the input RGB image, you initialize as empty your feature outputs and classifier outputs, and then you iterate through the different layers in the model. So this is as you go through the different, self.model.features.modules.items. You can go through them all, and you can put X through the module and rename it X again. So you're just putting X one layer at a time through this network. But after each layer, you stop and you check, is the name of the layer I just put it through, is that in my feature layers? If so, add X, the output, to my feature output structure. So I'm just sort of sticking into there whichever feature outputs I want to see. Then we'll go through the average pool layer. We'll do this flattening so that we can go through our classifier layers. And we'll do the same thing for the classifier layers, just go through them one by one, and we'll append classifier outputs that we want to see. Okay, so this is what happens. So here's just one of the images. This is one of our elephants. Red, green, blue, channels 0, 1, and 2. When we go through that first layer, now we can't print out all of them. I'm only showing you 4, the first 4 channels. You can see that what what we get still looks like an image. Looks like what's happening in those early kernels. It's doing some sort of maybe edge detection, like a vertical edge detection, something like that. They're obviously all a little bit different, but here I can kind of see some edge-like structures vertically. This looks, I don't know what that is. That's maybe not edges, but you can sort of notice that there's still a match between these images and the original elephant. Once you get to layer 10, though, so first of all, you have things that are 16 by 16. But at this point, even though these are images in the sense of having vertical and horizontal pixels, they don't look anything like the elephant anymore. Right? They have sort of a different meaning, because as you go through the network, you gradually go from space of images to pure feature space that is just to do with these 1,000 classes. So here we are pretty deep in the network. It's hard as a human to really interpret these, but it's something about some sort of information that was useful for classifying into these 1,000 ImageNet categories. Okay. But here we have a little piece of code that we can look inside any network and extract the feature maps just to visualize them. Okay, so that's what we did here. Any questions on these? Okay. So I think today I'll just cover one more slide, and then we'll have a short lecture on Wednesday, because there's really not too much left to cover in this unit. But so at a high level, everything we've talked about all unit has really just been about image classification, which is just like scratching the surface of how deep networks can be applied to images. It's just one very particular, very simple thing. So image classification is what we focused on. So let's talk about other things we could be doing, variations on image classification. So one is, let's look at this picture. One of these we did talk about briefly before, which is classification and localization. So it's a lot like image classification. So, okay, image classification, as we know, you're given an image and you want to output a single label, which is some category of what you think that overall image represents. So in this case, even though there's grass and sky and some hill in the background, we might say, no, this is really an image of a cat. That's the thing that's jumping out at us. You can go one step further and say, okay, this is an image of a cat, and in particular, I'll tell you where the cat is located. I'll give you a bounding box, which requires basically 4 numbers. The anchor, and the sizes. So now I know it's a cat, and more than that, within the image, the cat is located here. Okay, so that's a little bit more than image classification. You can take this further to object detection. In object detection, you do this, but instead of having a single category for the entire image, you have a list of categories. Usually not too many, maybe like 3, 5, maybe 10, not so many. So in this image, you're saying, okay, I have a dog that's here, I have another dog that's here, and I have a cat that's here. So there's some famous networks that do this. One of the more famous networks is called YOLO, you only look once. It's very interesting how they design this network. The architecture is not really that different from the networks we have seen until now, in terms of starts with images, puts through conv layers, pooling layers, and it shrinks the information down to classes and bounding box information. What's really clever about how they did this is how they did the loss. The loss is very intricate and very interesting. It's really like crafting the loss very carefully is how they were able to do this. The architecture is not so different from what we've seen. Now, there's another, so we've sort of talked about detection and classification. So another kind of famous task is segmentation. So segmentation is kind of different in that the output, in this case, is a specific category for every pixel. Okay, so like in classification, there's a single categorical output for the whole image, whereas in segmentation, there's a categorical output for every single pixel in the image. So in advance, you have to say, these are my list of categories. Usually, it's not going to be 1,000 of them. Usually, it's going to be some smaller number. Like, in this particular example, perhaps you said, there's 4 things that I know about. Grass pixels, cat pixels, tree pixels, and sky pixels. So now, given an image, tell me, for every pixel, which one of those it is. So that's segmentation, or more precisely, semantic segmentation, because there is another version of this over here, which is instance segmentation, which is sort of like a little bit like a hybrid of these two, where you're saying there's a list of objects, and for each object, I will tell you which pixels define it. So all these red pixels define the dog, the green ones, this other dog, and so on. So for these networks, the architecture needs to be quite different because the output size of this network is the same as the input size. So you can't have a network that takes images and boils it down to like 1,000 classes. No, it takes images and it outputs something like images, but now instead of a real number, it has maybe a categorical label for every pixel. So for these networks, they really do have a very different architecture than what we've been looking at. And the most famous one for this is something called the U-Net. And the U-Net has it has different branches. Basically, it works sort of at different resolutions where it has, as you go down these different branches, they make the image smaller. They subsample it so that what you have in this bottom branch is a very subsampled version of the image. In the top branch, you have maybe no subsampling at all. And within each of these branches, you'll have conv layers, ReLUs, the usual stuff. Over here, instead of downsampling, you're going to be upsampling back up to the original size. So that's what U-Nets look like. Okay, so those are a couple things you can do with images. Any questions on any of these? No? Okay. Other things you can do are totally different. Compression. So, we're familiar with algorithms for compression like JPEG. You want to represent an image with as few bits as possible so you can easily transmit it, store it, whatever. Well, not surprisingly, you can do that really well with a neural network if you come up with the right architecture and loss and everything. You can do much better than JPEG. Then there's a bunch of applications where you want to somehow restore the quality of an image. You get a corrupted image, and you want to recover the uncorrupted image. So maybe the corruption is noise. Maybe you get a really noisy version of an image. You want to clean out that noise without making the image look blurry. Like we know, we can convolve it with one of these blur filters, gets rid of the noise, but then the image looks really blurry. So can you give a sharp image, but without the noise? Another application is, well, somehow, for whatever reason, you got a blurred image. There was a famous example with one of these telescopes that they sent up into space. I think it was the Hubble telescope. There's a problem with the mirrors that they didn't realize that there's a problem with the mirrors until it was already up there, and then all the images were coming back blurry. So now you can't go fix the lens anymore. So you got to fix this, in software. So that would be image deblurring. And there's networks that do a great job of image deblurring. Deblocking is the issue when you're watching, let's say, digital television, and there's some issue with the channel, and all of a sudden you start to see these weird blocking artifacts on your screen, right? Because essentially the decoder is saying, I don't really know what's going on. This is my best guess, and it looks like this terribly blocky thing. So you might want to have then a chip in your TV that sort of intercepts those blocky signals and says, I'm going to work on them, try to present to the user a cleaned up version so the user doesn't see any of that blockiness. So that would be a deblocking network. Then you have other sort of related tasks, super resolution. If I give you, say, a 64 by 64 image, and I want you to zoom that up to a 1,000 by 1,000 image, if you did that using traditional methods, you would just get this big kind of blurry looking image. So the question is, can you zoom up and get really sharp edges and all these details that were missing from the original image but look very plausible to a human? So that would be super resolution. Then there's a bunch of problems that show up in medical imaging and other applications where you measure some version of the image in another domain, like the Fourier domain. So that's what happens in magnetic resonance imaging. You actually take measurements in the Fourier domain. And if you take enough measurements in the Fourier domain, it's as simple as taking an inverse Fourier transform. You get back to the image domain, and boom, you have this really nice MRI image. But the problem with that is that it takes a long time to sample an MRI. If you use these traditional methods and you put a person in the scanner, they might be in there for like a whole hour waiting for this exam to happen because the way that they collect the data, it just takes a long time. So to speed this up, to ease patient comfort, to put more patients through these scanners, which are incredibly expensive, they collect a fraction of the measurements needed by that Fourier transform. Maybe they collect a quarter or an eighth. And so now, from those measurements alone, if you just took an inverse Fourier transform, it would look terrible. It would have all these aliasing artifacts. So instead, you use deep learning to say, well, actually, I know quite a bit about what the clean images look like. Can I somehow combine that with the information I have from these measurements, put them together to get a nice clean image? And we've seen an example of this with map estimation, where we said, okay, we have this likelihood term, which would be the measurements. We have a prior term. It's not going to be lasso or ridge. Now it's going to be my prior is a huge collection of clean MRI images, and I want to put prior and likelihood together to get a posterior, and then maybe pick the most probable image from that, the map estimate. So we can build a deep network to do that. Phase retrieval is another one where in the Fourier domain, you get to measure all the amplitudes or the magnitudes, but you don't get to see any phases. And this shows up in optics. So in optics, it turns out lenses sort of do a Fourier transformation in the far field. And there's a lot of applications where, like building a microscope, where as you want to make this microscope more and more powerful, eventually the thickness of the lens gets in the way of what you want to image. You would like to get rid of the lens entirely. And that is possible if you somehow do this lensing in software, algorithmically. But now, when you build these sensors, they're usually sensing the image brightness, not the phase. So you're working with a sensor that tells you brightness, which is sort of telling you Fourier magnitude, but not phase. So how do you get around this problem? So that's what phase retrieval, that's that problem, and that's also something that people work on with these deep networks. The last one is in painting or image completion. So let's say that I give you exactly this image, which has, this nice scene in there, but it has this big red box in there, and you're like, I don't want that big red box in there. I want to get rid of that. So it's pretty easy to figure out, which pixels have the box that you want to get rid of. So you can tell the network, okay, wherever you see red, fill in what should be there based on everything else in this image. So this should all look like blue sky. This should look like the hills behind, but it should look convincing. It should look, the grass should look exactly like grass. It should be consistent with the grass around it. So that's in painting. And that's another problem that you can work on with these deep networks. And this is a lot of what my research group works on, is all this kind of stuff. Okay, so basically, like I said, for some of these networks, we have convolutional networks like we've seen. For other ones, we need things like UNets. But then there's even other networks that are very interesting that have very different architectures, like there's recurrent neural networks, where you have a network that takes in an input, gives you an output, but then that output is actually fed in again, and you kind of cycle the data around and around and around through this single network. There's improvements on those called long short-term memory networks, and improvements on those called transformers, and transformers now are what's powering all these large language models. So they have a very different, they're not doing convolution at all. They're doing something called attention. It's a completely different idea that can have advantages, especially in some applications. Okay, so I think that's enough for today. We'll talk a bit about generative AI next. We'll go through some of the main ways to generate things, but we'll save that for Wednesday. See you guys then.